Have you ever just looked up at the night sky and wondered what all of this really is?
What if everything you see out there, every star, every galaxy, our own little planet,
What if this whole cosmic show is just one tiny speck, floating in some other dimension we can't even begin to imagine? It sounds like something out of science fiction, right? But believe it or not, this idea is rooted in some of the most advanced, mind-bending physics of our time.
Okay, let's really dive into this. We're all used to thinking about the universe expanding, with space itself being created. But what if it's not about creation? What if it's about probability? What if the expansion of the universe is actually a quantum phenomenon?
And this right here perfectly illustrates the difference. The standard view, that's the one we all know, right? The balloon. You blow it up, the dots on the surface get farther apart. Simple. But this new quantum view, it's more like a ripple spreading out in a pond. The universe isn't getting more stuff. Its wave of probability is just spreading out, becoming less certain, more diffuse as time goes on.
And look, this isn't just some fun thought experiment. It's actually grounded in a real thing called the Wheeler-DeWitt equation. It's a serious concept in theoretical physics, and what it does is it treats the entire cosmos, all of space, all of time, as one single quantum object with a wave function we call psi. Just think about that. The same math we use to describe a single tiny electron could potentially describe our entire universe.
So a wild claim like that needs some serious backup, right? Is there any actual mathematical evidence to support this? Well, let's play detective and look at the evidence. We've got 3 key exhibits from the strange and wonderful world of theoretical physics.
Exhibit A. This is where it gets really weird. It turns out the math describing an electron and the math for a very specific type of tiny, rotating black hole, they're almost identical. It's spooky. Back in the 60s, a physicist named Brandon Carter showed that an electron has the same 3 key properties, mass, spin, and charge, as this type of black hole. And the math for that black hole suggests its singularity isn't a dead end, it's more like a doorway to a whole new region of space-time, a new universe.
But that brings up the obvious question, right? How in the world could our massive universe fit inside one tiny particle? Well, that's Exhibit B, Bag of Gold Spacetimes. And no, that's not just a cool name. It's a real geometric concept that might just solve this paradox. From the outside, you see a tiny particle, but on the inside, you could have a vast, even infinite amount of space. It's like a cosmic TARDIS. From the outside, it looks like a particle being born, but from the inside, you'd experience the Big Bang.
And for our final piece of evidence, let's talk about the multiverse. You probably heard of the many worlds idea in quantum mechanics, right? It says a particle's wave of possibilities never actually collapses into just one reality. Instead, every single possible outcome happens, each one branching off into its own timeline. So, if our universe is a particle, then its wave function isn't just our history, it's the collection of every possible history, every alternate timeline. It is the multiverse.
Okay, so if this theory holds any water, it has some pretty huge implications, especially for how it all ends. You know, particles decay. They have a lifespan. So if we're a particle, our universe must too. And the really wild part is that our ultimate fate, the end of everything, depends entirely on what kind of particle we happen to be.
And just look at how different the predictions are. If we're like a heavy boson, we should have decayed in less than a second, which would mean we're just living inside that split-second explosion right now. Weird. If we're like a black hole, where more mass means more stability, then our universe is basically immortal. It'll just slowly evaporate over a timescale so long it's functionally forever. Or, if we're like a radioactive nucleus being torn apart by expansion, we could be headed for a big rip in about 22 billion years.
An idea this big, this elegant. Well, it has to be put on trial. Does it actually hold up against what we observe in the real world? Let's put it to the test and fact-check the claims.
All right, fact check number 1. This is a big one. The whole idea kind of hinges on an electron being like a tiny black hole. But for that to work, it needs an event horizon. Problem is, the math shows an electron spins way too fast. That spin would basically create something called a naked singularity. And according to general relativity, that's a huge no-no. It would completely break the laws of cause and effect.
Next up, the forces just don't add up. Think about the forces holding a normal particle together. They are incredibly strong. But gravity, the force holding our universe together, it is ridiculously, unbelievably weak in comparison. We're talking 10 to the power of 40 times weaker. The theory offers no good explanation for this enormous gap.
And here's a crucial point. Is it even testable? Science demands that a theory must be falsifiable.
There has to be a way to prove it wrong. But by its very definition, we can never interact with the other timelines of a multiverse. So if we can't measure them, does this idea leave the realm of science and cross over into philosophy?
There's also a big conflict with dark energy. A simple quantum wave spreads out, sure, but that spreading either slows down or stays constant. Our observations of the real universe show that its expansion is getting faster and faster. That directly contradicts the analogy, unless there's some unknown external force from a bigger superuniverse pulling us apart.
And finally, there's a geometry problem. Particles are finite, contained objects. But our best measurements tell us that the universe appears to be perfectly flat. And a flat geometry implies it might be infinite. Now, this doesn't totally kill the theory. We could just be on a particle so huge it looks flat to us. But it's another significant challenge.
So, after putting this theory through the ringer, where does that leave us? We're left with an idea that is both deeply compelling and deeply challenged. It's a perfect testament to how we try to make sense of our place in the cosmos.
So here's the final summary. Is the particle universe theory impossible? No. Is it proven? Definitely not. But here's the key. Is the math behind it sound? Yes. It's a valid candidate for a theory of everything because it does something incredible. It elegantly combines the physics of the very large, black holes, with the physics of the very small, quantum mechanics.
And you know, in the end, the theory's greatest hurdles are also the biggest mysteries in all of physics. If it could somehow explain why gravity is so weak and why cosmic expansion is speeding up, it wouldn't just be a clever idea, it would be the answer. And that is a possibility absolutely worth exploring.